everybody from wherever you are. My name's Luke and I'm here to introduce this webinar, which is on 5 ways reliable temperature measurement improves process safety, product quality and business performance. I'm here actually just to introduce a couple of global experts that we've got from Germany for this particular webinar. Firstly, we have Benjamin Lucas, who's the training manager for temperature at Wetzer, which is our factory for temperature measurement in Germany. And secondly, we have Dietmar Secker, who's asked me to introduce himself as the all-knowing temperature guru, who's also known as our senior applications manager for temperature. So that's it for me, guys. I'm going to come back in at the question and answer session at the end. We've got a really highly interactive webinar for you all, so I really hope you enjoy it. I'll see you all soon. I'm just going to hand over to Benjamin right now. Ben, or Dietmar first. Hello.
Hello, good morning. This is a live broadcast from Germany. It's quite early in the morning here, so really a pleasure to present the temperature measurement. Yeah, the all-knowing trash bin is something you maybe know if you're in my age. It was Fraggles. It's kind of a Muppet show, and there was a trash bin which is asked by the Fraggles. So, and I'm doing temperature measurement for almost 30 years, so that's the reason some guys call me like that. Together with me, this is my colleague Ben. So he's not really there. It's a electronic effect. We are in the same room. So you know also Germany is affected by the global crisis, so we are safe. There's a big distance between us, and we both together like to present some words about temperature measurement. My record is I did a 5 hours presentation for Nestle 2 years ago, so 45 minutes for temperature measurement. It's a hard ride. So, yeah, Ben will introduce the interactivity of this meeting.
Yeah, just very shortly. Hello also from my side. Great, you made it. Great, you are here. And the main thing that I would like to focus on now is that we try to have this session as interactive as possible. So therefore, you just saw a QR code, or you see it here, and you can also see it on this slide. So could you please scan that QR code, or go with either smartphone or with your web browser on www.menti.com and enter the code 5635 and 3. No installation, no app download, totally free, so also data secure, and it would be great to get your feedback in our session because we don't have a recording but a live webinar together with you. You will see that QR code during the presentation, so no need to do it right away. But the first question we ask to you is something where we see your live feedback right here already. So why do you measure temperature? Please tell us, let us know, and we see some incoming.
Energy saving, yeah, good. Control, quality, optimization.
Looks good.
Yeah.
So, for all of you who just recently joined, please join us on www.menti.com and use the code 56353. On the slides of Dietmar, you will also see the QR code for a couple of more minutes. And it looks good, people coming in. Process condition.
Absolutely cool.
Keep the process in spec. Okay.
Yeah, energy saving is good. We will definitely focus on that. On quality and control, definitely also. So good. It seems to be that we have chosen the right themes for today. So let's start, I would say. Thank you very much. So what we will cover today is 5 ways to optimize your temperature measurement, and we also talk about the vibration resistance of the thermometer itself. We will definitely talk about response time, which is related to safety and also for energy saving. We will talk about calibration and how you can make your temperature measurement more accurate. And as mentioned, the accuracy is not only based on the quality of the sensor itself, it's also about the engineering of the temperature measurement, how you install it. This is one of the focus. And for sure, there is an influence of the electronics, and there is a wide variety of different electronics for temperature measurement. That's what we will focus on today. And probably you will know a few things about temperature measurement, and wherever you go in the world, to every supplier, you will know that there are two widely spread ways to measure the temperature. Using RTD measurement, means a PT100, we come to this, and you will see that there is a standard thin film sensor. We will have a detailed picture about this, and the wire wound sensor for measuring temperature using an RTD. On this thin film thermometer, you will have a that's the name saying, a film of platinum, which is sputtered to a ceramic plate. And in a wire wound sensor, there's really a wire made of platinum, thick as a hair more or less. And if you break it and you spread the wire, it's nearly 1 meter long. So very thin wire in this ceramic body. The temperature measurement using an RTD, you might know, just for repeating, is RTD means resistance temperature detector, and the most common way is a PT100. PT for platinum, the most stable material in the world, and 100 for 100 ohm of electrical resistance at a temperature of 0 degrees, which is a temperature of melting ice. And the resistance is increasing if you increase the temperature, and that's the reason it's a PTC, positive temperature coefficient, hard word. So means 100 ohm at 0 degrees Celsius and around 138 ohm at 100 degrees, the temperature of boiling water. And the wiring diagram, simplified, you need an energy supply and you measure the resistance using the well-known formula U voltage is resistance multiplied with the current. So this is a way everybody knows, and these are detailed pictures of the two general sensor types. The ceramic wire wound sensor has a total length of approximately 15 to 20 millimeters. And as mentioned, you have this thin wire going up there, then it's connected, and another wire is going down so that you totally reach 100 ohm. And on the thin film thermometer in the sensor itself, the ceramic plate is white, and what you see here in a little gray is the thin film of platinum, which is going up and down until you reach a certain length, which reaches to 100 ohm. We use, and all the colleagues use, mainly this thin film sensor. You can immediately see it's smaller, so it's easier to work with it, and the sensitivity is on this chip. And on the wire wound sensor, you will more or less measure the average temperature of this ceramic body. And we will come to this in detail because this is changing the properties of a thermometer. The big benefit of a wire wound sensor is the temperature. Maximum temperature you can measure is 600 degrees. And the maximum temperature of thin film sensors is limited to 500, 400, or 200 degrees. It depends on the installation. So, additional to RTD sensors, PT100, we also offer thermocouple measurements. And thermocouple measurements are used mainly for temperatures which are outside of the specification of a RTD sensor, which is 600 degrees. And a thermocouple is working totally different. Instead of measuring a resistance, we are measuring a voltage. And this voltage is produced, more or less, because you just weld together two different metal materials. So the most common material mix is called thermocouple type K, which is One line is nickel and the other line is nickel together with chrome, so an alloy. And this effect happens all the time if you weld together two different metals or different alloys, and then a voltage is produced. So you don't need an energy supply. The energy is coming outside of this thermocouple. And to demonstrate this, I have prepared an experiment, and probably you're sitting at home, and don't do this at home because you need heat a lot, and you need a thermocouple. You can make your thermocouple at home with aluminium and a wire. And this is a voltmeter because I'm in a certain age. In my private equity, I have a 60-year-old voltmeter, so there's no battery. It's just a voltmeter. And you see the scale is made in degrees Celsius. And here we have a thermocouple. So it's dangerous, but I have trained this. So if I heat up the tip of the thermocouple, so I shouldn't burn the camera, you see the temperature is increasing a lot. We have 400 degrees, still the, so you see, so we are producing a voltage which is very small. It's 20, 30 millivolt, and this is directly indicated here. And now the sensor tip is red glowing, so the benefit of a thermocouple, it's totally robust because you just weld two metals together and that's it. And now we have reached more than 600 degrees, so we are out of the spec of a RTD measurement. So this is a thermocouple, and remember, don't do this at home. And now it's dangerous because it's red glowing. And I'm back again. So you can use this for waste incinerators, burning processes in refineries, and so on. So if you exceed 600 degrees. Additional to this, you have seen the thermocouple is quite robust. Additional to this, Endress+Hauser has invented a number of different ways to measure the temperature using an RTD, which are also touching the thermocouples, especially the strong sense. Sometimes thermocouples are used because you need very robust sensors, vibration-proof, shock-proof, and so on. And we have invented something it's called strong sense, which is used for high vibration applications. Additional to this, we have a thing called quick sense, and here the thin film sensor is connected directly inside the tip of a measuring insert. And here the strong sense, the thin film sensor is inside a kind of concrete inside the tip. And then we have the very famous trust sense, the self-calibrating temperature sensor. That is where I talked 5 hours with Nestle about it. So this is too much for the presentation today. If you are interested in this, ask our colleagues in Australia, so maybe we can make an additional webinar for doing this. And let's talk about the strong sense, the vibration proofness. Ben has prepared a kind of question. Do you have an impression what is mean with shock proofness? So, Ben?
So, yeah, when we talk about the strong sense, we need to talk about how much G we use to test that. And now it's interesting for us what you have for a feeling kind of. So we have those different scenarios. So an explosive seat ejection from an aircraft, we all can imagine that. A space shuttle during launch and re-entry, a car crash with about 60 miles per hour straight directly to a wall, or an F-16 aircraft pulling out of dive. And could you please give us an indication what you think, how much force is applied in those different situations? Because I think it's maybe good to know, so we will get the answer to that in a second. And then we get a little bit of more grip to the comparison of what our sensor can do, what a regular sensor can do, and how that might help you lower your costs for example, replacement of sensors, and of course increase the process safety.
So the questions are, the answers are coming in.
Yes, and we might also directly have a look at that. Okay, so about 15 G for the aircraft, about 10 to 15 for the space shuttle, about 15 for the car crash, whereas that is a rather broad range, and the F-16 with about 10 to 15. So more or less all of them the same according to your feedback. Dietmar, let's see what the reality looks like.
Yeah. So the reality is that the space shuttle, I was surprised when Ben told me it has 3G only. So the F-16 is 8G, and I think some people get unconscious, yeah, bad word for in German, if they do it. So explosive seat from aircraft 15G, and car crash against the wall is 40G. All right, the sensor we have produced is able to survive 60G, which is a car crash with 90 miles per hour. So if you do this, the strong sense will be okay, you probably not. And what is the normal, what is written in the standard, which a thermometer must survive, is 3G. So it's 20 times more robust. So you can use it as a piston compressor and applications like this. And this is also relevant if you have safety critical measurements, because whatever you do, this would be a low stress environment for a strong sense RTD thermometer. So we have spent a lot of effort to develop this. And the story behind it is we have a test bench to try this, and unfortunately this is limited to 60G. So in fact we don't know how robust it is, because with this shaker test bench at 60G were not able to destroy the sensor. All right. Additional to this, we have the quick sense. As mentioned, it's the sensor itself. The RTD chip is connected to the inside of the measuring insert, and we come to this in a video. We are measuring the response time of different RTD measuring inserts with a bath. So this is a bath with warm water, and this is whirlpooling around. And we dump the probes into the water, and we will see the result. So here we cool down the probes, so different designs. This is our calibration lab. And now we dump the thermometers into the water. And then we see the different time response of these installations. You see here, so one is very fast, it's already finished, and the other one is still growing. And this behavior, so we have invented the quick sense and other innovations to make the measurement as fast as possible, because this is an energy saving and safety issue. If you imagine that you have a process which is going up and down, or slowly or fastly increasing, so the red line is the real temperature, and it depends how fast your temperature measurement is, which is the delay between both. And as faster your temperature measurement is, as closer you are at the real process temperature. And that means if you have to control a certain value which you could not exceed. For example, if you produce milk and you are too hot, you will taste it. Or if you have a safety critical issue and your thermometer is too small, you might already have an explosion until your temperature measurement is seeing it. And so this designing the temperature measurement to be very fast is a quality and safety issue, and also it's energy saving, because if you should not exceed this temperature, you can save energy. And so in saturated steam, for example, if your temperature measurement is faster, so the delay between both gets closer. That is a lot. We spend a lot of effort to this, and we will also publish some papers about it in the next months. So this quick sense might be a solution for applications like this. So the trust sense, as mentioned, is too complicated for a 45 minutes session. And the question for us is if you have ever heard about it, about this self-calibrating temperature sensor for food and beverage and pharmaceutical industries. This is the next question Ben will.
Yeah, and it's already open. So please tell us, have you already heard about the fabulous iTherm TrustSense, the world's first self-calibrating thermometer? And we already see some trend in there. So together with the recording, you will get a link to a short, about 6 minutes YouTube video that is explaining the measuring principle of TrustSense in brief. And if you need any further information, of course, all our colleagues worldwide, so your local Endress+Hauser colleague will be more than pleased to help you out with some further knowledge. As Dietmar said before, he had a presentation at Nestle about 5 hours talking about just this sensor. So that would
totally exceed
everything we have. And once more, for those who are not connected yet, maybe someone came late, join this interactive part with your smartphone or your tablet or your laptop via www.menti.com and the code 56353. So,
okay,
back to you.
Thank you very much. So the next question to you, we are entering now this accuracy part. So when you think about accuracy of a temperature measurement, what are the words which come to your mind at first? So please enter them into the Mentimeter. Correct, Ben? Yep.
Totally correct.
Resistance, percentage. Impossible. No. Yeah, total. Yeah, it's a philosophical issue. Total accuracy is impossible. That's right. You will always have a measuring uncertainty. So, philosophy for me in the early morning, for you in the afternoon. Great. Sampling rate, resistance, reliability, repeatability, hysteresis.
Sensor class.
Sensor class. Have you seen it? It's so fast.
It's great that you give so much feedback, because that's actually how this presentation lives. And
you see, it's alive. It's not recorded somewhere.
Right.
Hunting.
gives
Hunting.
the
Pizza.
for that.
Good. Yeah, pizza temperature is very important. That's right.
You also see we don't have a word filter inside, so please don't abuse the possibilities you have.
Variation, resistance, certainty, certain standardization, sensor class. Great. Yeah. We can work with this. All right. You all know probably the accuracy classes of temperature measurement. This is written in a international standard 6751, and here you have the classes B, A, and AA. Just some words. What you also always see here, the best accuracy of an RTD sensor is at 0 degrees Celsius, because it's so easy to make. And as far you go away from the melting point, the inaccuracy or the tolerance is increasing, and then it's the question if you have a B, A, or AA sensor, which is limiting this funnel of tolerances. And also very important, how you connect the sensor. We totally don't recommend the two-wire connection because you will always measure the resistance of the RTD sensor together with the resistance of the wires. That makes a permanent mistake, and this mistake can also change by the temperature because the wires themselves change their resistance in a way. So the 3-wire connection is okay, and the 4-wire connection is what we call a standard. If we produce our sensors on our robotic manufacturing site, they are always in the 4-wire connection method. If you want to connect it in 3 wires, you can do it, but that's what we call a standard. But in total, the accuracy of the sensor itself is not the limiting factor of a temperature measurement. The factor is really the way you install it. And I would like to focus on this. I call this golden rules for contact thermometers, because the temperature measurement can only display the value which is seen by the RTD sensor somewhere in the middle of the thermometer. So there is an energy flow from your process to the sensor, or for cooling process in the other way around. And so because for our industries, your core business, most of the thermometers are made of stainless steel or something, so we have a metal connection. So that means there is some heat transfer from inside outside or the other way around. And please consider the RTD sensor is located somewhere in this installation. You might understand this if we go to this picture. If you think about a process, for example, sterilization, which is hot in the inside, 120 degrees Celsius, and you would touch the flange, you would see, yeah, it's hot. So it's not the ambient temperature here, it's something else. So we have convection from the flange to the ambient, and we have metallic conductivity of energy inside this installation. And to give you a rough overview, just imagine this. If you measure the temperature of a process which is hotter than the environment, you can imagine, okay, we have 20 degrees, or in Australia, 48 degrees on the outside, and you have 120 degrees in the inside. So think about what is in between. As mentioned, if you would touch the flange, it's hot. So the reality is in a simplified way like this. Along the neck tube, here the heat is increasing, the flange is so hot that you can't touch it, and somewhere here you will reach the process temperature. And also in this part between your process connection, the flange or the thread or whatever, and the position of the sensor, there is a gradient inside the stem. And we have to look on this because this is a position where the sensor is placed. And now think, we offer different solutions. The ENH Quick Sense, ENH Strong Sense. Here the sensor is inside the tip of the measuring insert. Here we are already 5 millimeters away. For the standard sensor, we are talking about roughly 10 millimeters. And for this wire-wound sensors, which are quite long, you will measure the average more or less at this position, 15 millimeters away from the tip. And now going back to this gradient inside your installation, it's a different if your sensor is really placed close to the tip, like using the Quick Sense, or it's a little bit behind, or especially if your wire wound sensor is measuring the average at this position. And so that means if this is the process temperature, using a sensor on tip technology, you are very, very close to this value. And if you take a sensor which is measuring at a different position in an installation like this, your mistake, the measuring mistake, is much higher. And this, we are talking about a few degrees if the installation is not perfect. These effects are much higher than the accuracy class of the sensor or 3 or 4 wire connection. So what can you do against it? Because most of the customers and applications are interested in a very short insertion length, if you have a small pipe or whatever. But this results in a very steep gradient and a quite big mistake. If you manage to make your sensor installation longer, you see the gradient is less steep and the mistake is smaller. Instead of this, you can decrease the permanent mistake to a smaller value. So size matters. As longer your installation is, as smaller your mistake is in an application like this. So what can you do to make your measurement better is, make your measuring insert, make your thermal well longer. And you can do this, for example, by an installation like this. So the second best method is not going 90 degrees rectangular, just place your installation with an angle. So your sensor is longer, your gradient is less steep, better. And the best installation is if you go into an elbow, because then there is no geometrical limit of your sensor length, but for sure you have to consider a thermal well calculation because a longer sensor has a different wake frequency. Also a quite complicated thing, just to keep in mind. To make it accurate, the sensor should be, the measuring insert should be quite long, but there might be a limitation coming out of a thermal well calculation. And if you consider this, what you have learned now, I want to show you something. We have also invented quite interesting T and elbow pieces, especially for hygienic industries, machined from one block. But if you think like this, what would be the best installation? What kind of sensor you would place into one or the other if you need to reach the best accuracy? Okay.
So actually Dietmar is waiting for a question which we don't ask right now, but we will show you.
We will show. Okay. If you think about the elbow pieces, which is here, and for example, the flow is coming from here. And here we have the T pieces. If you just place a standard sensor into a T piece, the sensor position might be here. So you won't measure the temperature of the flow. You measure a kind of average between your process temperature and the ambient. So we have tested this on test benches, and we are talking, if we have 120 degrees of steam temperature and 20 degrees on the outside, we are talking about delta of -3 to -4 degrees. So if you instead use a quick sense, where the sensor is located here, you are much closer to the reality. If you go to an elbow pieces, you can easily imagine if your sensor is here, it has a chance to see the process temperature. So the results are much better. Also here, using the sensor on tip technology brings effects, but the difference is quite small. In this case, we are talking about here 0.3 degrees, and here we are really close to the process temperature inside 0.1 of Kelvin of deviation. So if you need to install something in T pieces, you should always take the sensor on tip technology. So it's always better to install this temperature sensors in small pipes in an elbow piece, because you are closer to the reality. And that's just physics. E&H is a big company, but we cannot change physics, so that's the way to do it. All right.
And just to complete that story, if you need to do it 90 degrees, think about the stability of the thermal well, so a thermal well calculation, maybe according to a standard, but also think about to increase the length as much as possible. So to be accurate, if you need 90 degrees, it needs to be as long as possible. So think about that.
Okay, now if we have talked about the best way to install it, for sure we have to talk about what to do with the signal. Now we have an ohm signal from the PT100 or maybe PT1000, and we have the millivolt signal coming from a thermocouple. That's not what we want. We want temperature. So we need something, a kind of transmitter, to transfer this raw data into a temperature reading. And this is the job of the temperature transmitter. And on PT100 measurements, we have prepared some additional information. This characteristic curve of a PT100 is written in the standard, and it's nearly linear. It's not totally linear. And we have seen on this funnel slide, there is a tolerance class which is written in the standard. And this standard is more or less the average of these PT100 sensor itself. But in the reality, every sensor might be a little bit different. And this is leading to some kind of inaccuracy. First, the curve is not totally linear. We will see it. It's a little bit curvy. And if you do a test, you might see that a standard thermometer has a tolerance, like written in the standard, of a few milliohm. You expect something around here, 138.2 at 100 degrees or 0.5. So it's inside the tolerance, but it leads to a small deviation. And so if you want to avoid this small measuring error, which is still in the tolerance, we can do something which is called sensor transmitter matching. And I have to explain this in a little. So the real curve of a PT100, it's written, it's based on this equation. And you see here, R0 is a 100 ohm value. So in the reality, maybe this is not exactly 100.000, it's maybe 99.9 or 100.2. And this is multiplied with some factors, A, B, and C, but C is only relevant for negative temperatures. So A is multiplied with the temperature, so linear, but you see this B is multiplied with a square of the temperature. This makes the characteristic curve a curve. And if you do a calibration inside a calibration lab, you can identify the individual values of every sensor. So you measure the R0 at 0 degrees in an ice bath, and based on different next calibration points, you can determine the factor for A and B using the calibration. And then you feed these values into the transmitter. So you tell the transmitter, hey, transmitter, there's a sensor connected. We have measured it. Don't use the standard values. Use these values to recalculate the temperature based on the resistance you measure. So what the transmitter does is the inversion of this curve. And this is called sensor-transmitter matching, and this equation is called Callender-Van Dusen because these scientists have identified the behavior of these sensors. And the effect is that an individual sensor can be made better than the standard class. And this is called the sensor-transmitter matching. But also that means if you disconnect this marriage between the sensor and the transmitter and just connect something else, the effect would be bad and not predictable. You will be worse than the standard sensor if you do this, but you are better than the standard if you do this sensor-transmitter matching. So in totally, you can reach a kind of not that the tolerance class is going outside. If you go far away from 0 degrees, you have a constant. That was the word I'm missing. You have a constant inaccuracy during inside the measuring range, which you have calibrated. So you are going away from this funnel to a constant inaccuracy in your measuring range. That is the benefit of the sensor-transmitter matching. So next thing we have to talk about is, now we have a digital value inside our transmitter because you can imagine that all of these transmitters are digital. So usually you go further on with a 4 to 20 milliamp or with a digital communication. And this has also effects. We made a measurement for this. If you use 4 to 20 milliamp, you have 2 additional signal conversions. The transmitter is converting the digital value, which is inside the processor, to a 4 to 20 milliamp analog signal, and your DCS measuring insert card is reconverting this analog signal to a new digital communication. And these 2 conversions also have an effect, and it depends on the quality of your DCS. In an example we have calculated, the additional inaccuracy was half a degree. So we generally recommend to use the digital communication if you need accuracy, but the question is, are you doing this?
So, it's your turn again.
Okay.
Please show us. We haven't lost you in the last couple of minutes. Been tough, been a lot, but should have been understandable. So please tell us, what communication do you mainly use to transmit a temperature signal? You have the choice between hard, 4 to 20 milliamp, Profibus, Foundation Field Bus, or others, maybe IO-Link or stuff like that. Please tell us your feedback on that. And we see that it looks like, maybe what we assumed, right?
Yeah, absolutely. Close to this.
Okay.
All right.
Perfect. What we will show you now is not what you use, but what we sold so far in the last year. So maybe that shows a little bit a different image, but Dietmar will show.
So that's what we sold. 50% of the instruments we sell or we have sold in the last years are using hard. That means hard is mainly used for maintenance and parameterization of the instrument. So it's not used for permanent transmission. And you see the other 45% is just 4 to 20 milliamps. So, and the digital communication are 3 and 1% for Profibus or Foundation Fieldbus. So that means that also your, thank you for your values, the majority of the people, of the users, are not using the maximum accuracy. You will give away accuracy if you use analog communication. If you need an accurate measurement, you can save half of a degree or a little bit lower than this by using digital communication. And in the majority of the applications, temperature measurement is not too fast to use it for digital. Your temperature normally increasing quite slowly, so whatever of digital communication you would use, it would be fast enough for a temperature measurement for the majority of the application. So if you need really best accuracy, think about using the hard protocol for transmitting the temperature value. So that's what we recommend. Whatever you do, you can do because we have a variety of different temperature transmitters. 1 or 2 channel input with or without seal functionality, with or without ISC X approvals for hazardous areas, with or without display. I won't go to order code crunching now. If you have questions about this, please ask our colleagues in Australia. We permanently do innovations in our transmitter portfolio, so probably now surely you will find what you need for your application, digital, analog, and so on. Just to give an overview, you will see this in the handout for selecting the right order codes.
Just one basic information, because we asked this question kind of in the description of the session when it is about the safety of your processes, and when you talk about seal, the major factor or the only factor influencing that is if you calibrate and the transmitter. So we offer those 2 transmitters you see there, which are available with seal, and they can be, they can achieve seal 2 or 3 if you calibrate them often enough. Of course, there are many, many more measurements how to increase the safety of your process, whether it's the sensor or whether it's some additional features. So far about the transmitters. Dietmar, what you doing? I'm quite afraid.
No. You will have your quiz now?
Yeah, perfect. So basically, that's the presentation. For those who have the question about the presentation, we will send that to you together with the recording, so no worries. And right now, for those who are not connected to our Mentimeter part yet, please do so now, because we're having a little quiz. 2 small questions for you, whether you got the key messages we tried to deliver to increase your process safety and to increase your product quality and, of course, your business results. So therefore, you get some avatar, whether you like it or not. You can give yourself a name, whether you like it or not. And in 5 seconds, we will start that quiz with whoever is here. And it's just 2 questions. Who answers quicker gets more point, and we see who is the champion of temperature measurement for today. So,
Good.
5, 4, 3, 2, 1. There we go. First question. How can you improve your temperature measurement accuracy? 4 options: increase the neck length, insulate the pipeline, choose the right sensor, or increase the insertion length. Please give us a vote. And without spoiling too much, it's quite tough to get the wrong answer, but some of you got it. So therefore, the neck length got nothing to do with it. Of course, you could increase the insertion length, whether mounting at an angle or in an elbow piece, like Dietmar explained. The right sensor plays a vital role when it comes to that. And what we didn't touch, but what maybe came to your mind, you could also insulate the pipeline to get a lower gradient and therefore to get a more accurate temperature measurement.
Perfect.
But great for most of you. And second question, here we go. We're already 5 minutes late, but I hope you give us the time. After a sensor transmitter matching, which sensor is more accurate? So when we put the linearization curve of a real sensor inside the transmitter and we match them together, which sensor is more accurate? Is it class A, class AA, or doesn't it matter because both are equally accurate after a sensor transmitter matching? Nice. Class AA, in general, the more accurate, but as soon as we get this linearization curve, the uncertainty of the class doesn't play any role anymore. So therefore then it is all the same if you have a matched transmitter and a matched sensor. It is not relevant anymore whether it's a class A or a class AA sensor. Anything to add, Dietmar?
No, perfect.
Okay.
So
So that's it from that little part here. But now we come to all of your questions. And first of all, thanks for being here.
yeah,
Thanks
big
for
fun
having
for
us.
us. We hope you like it.
And Luke, thanks for joining us now for the question and answer session. And we have some questions here in Menti, which we could... Oh, we need the winner, sorry.
No.
Megan, congratulations. Perfect. The fastest. There are others who had the same result of correct answers, but Megan was the fastest with both answers correct. Congratulations. No prize, but the honor and pride of winning our little competition.
Great.
And now we have a couple of questions. If you have more, please just shout at us. RTD drift over time. Basic, simple answer, calibration.
Yeah, calibration by dismounting it, putting it to a calibration, or by using this self-calibrating sensor for special applications. But there's no other way to detect the drift than that you compare the result of the RTD with a reference. And the reference is a calibration environment or a physical fixed point. And so there's no other answer than calibration.
Next question. What can be done to detect fouling on sensor element thermowell? Or in German, Verschmutzung des Sensorelements.
Again, it's not possible to detect any kind of drift except you do this calibration because the electronic cannot decide if the change of a millivolt signal or the resistance value is coming because the temperature has changed or because the sensor in a way has drifted. And so unfortunately, there is no other choice to this.
Then how can we improve generator bearing temperature measurement? In our case, we have an RTD element in air or oil-filled pocket, not in direct contact with the bearing.
Perfect. So the best answer is already mentioned here. Oil-filled. If your sensor pocket is oil-filled, it's 10, 20 times better than just with air. As you can imagine, air is a heat insulator. And if you want to measure the bearing temperature, as mentioned, the sensor can only see the temperature which is at the sensor. And you have to get the energy there. And if there is an air gap in between, a lot of the energy will stop there and won't reach the sensor. So what is definitely good is that you fill the sensor pocket with oil. Water would be better, but water would vaporize in the way. So just fill oil there, silicon oil, or if you have food applications, take sunflower oil, whatever. So something which does not disappear. So you already have stated the answer yourself. Oil is perfect, air is bad.
We also have another possibility when it comes to using a thermowell, which is a fast-responding thermowell with a different material that stays in place. So therefore, we will also include a short video link in your feedback mail concerning that. Because, as Dietmar said, now we come back to the very beginning, Dietmar. When we talked about pizza, just think about a pizza guy. He brings your pizza in a styrofoam box, and that is isolating as well because there is a lot of air inside.
Yeah.
So therefore, we will include something there, and we have a sensor portfolio being shown here. Yep.
Yeah, and
it's getting sharp.
the other answer is here, the quick sense.
Yeah.
You see here where the sensor the RTD sensor is directly located into the measuring insert tip. And if you place this kind of sensor in your sensor pocket and fill the air gap with air, this is the best way you will get the best solutions.
With oil, not with
With oil, yeah, sorry.
No worries. Okay, then we have something else. Is there a rule of thumb for the selection of 3-wire versus 4-wire?
Yeah, I would say if 3-wire is okay for if you have connection cables from 10 to 20 meters or something, 3-wire is still okay. If you use mineral insulated cables, so if the sensor or the measuring insert we supply is 1 meter long or whatever, we already recommend 4 wires because the way to produce mineral insulated cables is very special and you cannot guarantee that all of these wires have the same resistance. And so for just cable, plastic cable or whatever, you can be quite sure that the resistance is very homogeneous around this cable. But for mineral insulated cables if you exceed half of a meter, I would recommend 4-wire.
Yeah. So, is there a guideline on the best insertion length for vessels, for pipes? Is it 1/3, 2/3 of diameter? Is this correct? What about vessels?
Yeah, I'm not so familiar with this application now. It depends, is there any liquid in it, steam? Then the insertion length is not very critical. For gases, it's complicated because the heat transfer rate of gas is quite low, and then you would need more measuring insertion lengths. But as mentioned before, yeah, if you would see a chance to make your insertion lengths bigger, you will have an effect on the accuracy.
But to make it clear, we saw that earlier in that one picture you will also have in the presentation. To get the most accurate temperature, the temperature of your medium is always in the middle of the pipe. So however you reach that point is up to you. So you can insert it at an angle or in an elbow piece. So that was basically what we put in our operating instructions. In the middle of the pipe you have the correct temperature of the complete process, because the further outside, of course, the cooler it gets because of this gradient that we saw.
Yeah.
But
then we have to talk about what is the flow velocity at this application. So there is no easy way to install this.
2-sensor transmitter might be a way to compare measurement to detect drift or buildup.
One of my favorite questions, definitely. But yeah, how much? So my working day has just begun. So a few words only. If you have, we often talk about dual sensors, so that you have 2 PT100s in the same measuring insert. So, and here, if 2 sensors are exposed to the same environment, the same going up and down with the temperature, the same vibrations, the same putting them out for calibration, putting them in again, so they are aged and exposed to any danger in the same way, it's more probable that they behave in the same way than thinking that if one is okay, the other might be broken or the other way around. So I'm not a real big fan of putting 2 PT100s in one measuring insert because, yeah, I don't see any safety benefit in this.
Yeah.
They will probably behave the same, and if one drift, give me a reason why the other one shouldn't drift. Yeah. So that is the reason we have invented the truss sense, where we have 2 totally different things put in one sensor.
Yep.
And the other way, if you want to use this, take 2 sensors, 2 different measuring inserts, and install them at different times. So exchange one of these and half a year later the other.
Yeah.
If they then behave in the same way, you have an impression that there is a difference between these.
Yeah. We go to one question from the audience with the other tool. So there was the question, CVD calibration, if it is done in the field, like for instance when I'm replacing the transmitter or the RTD due to being faulty in the field. So can that be done in the field by calibration?
This can be done. If you do for making a new CVD, you need a 3 or 5 point calibration. Yeah. Then you need to know how to calculate the CVD values from your calibration results, which is not very easy to do this. And then if you enter the field care, device care software with the right DTM, you can tell the transmitters the new CVD values. Yes, it's possible, but it's something for experienced calibration technologists.
Yeah. Furthermore, please also think about the inaccuracy that a in-the-field calibration brings with it. So in a calibration lab, of course, you can reach a higher accuracy. So that would be a better matching. And if you order, for example, a spare sensor together with a sensor transmitter matching, then you get a calibration certificate with those coefficients, and you can put that in the transmitter. And with our Bluetooth transmitters, for example, that's rather simple with a nice smartphone app to manage there. More, does the accuracy increase if we connect the thermocouple directly to DCS card type that accepts millivolt instead of having a transmitter in between?
Yeah, it depends on the quality of your DCS system, definitely. And you can imagine we are temperature measuring experts. We only do this. So we take care that our transmitters reach the maximum accuracy. And DCS card is more or less a standard input card. And what is also has to be considered here is if you use long cables for the thermocouple, they should be made of the same material, otherwise you get additional inaccuracy, and this is only possible if you have type K or some kind of standard thermocouples. And for higher temperatures, if you were talking about platinum thermocouples, you will have only compensation cables which bring additional mistakes. And so it really depends on the applications. For high temperature measurements, we recommend to install a temperature transmitter quite close to this thermocouples. And in general, yeah, I would think it would be better to trust on an expert there. And if you transfer, for example, only 20 millivolts with using a 50 meters cable, you also have a kind of an antenna. So the signal safety is better if you place your transmitter close to this quite small signal source.
One more thing, because right now I see that some of you need to leave because we are already 15 minutes late after what we scheduled. Thanks once more for being here. We have a couple of more questions. We have a lot of detailed questions about certain applications, and we or the colleagues in Australia will reach out to you directly, the ones who asked that question, to answer it in a direct chat. Maybe one more thing we might cover here is, is there any impact of attaching the sensor with a thermowell? So accuracy versus lifetime. And once more, yes, there are opportunities how you can increase, for example, the response time and the accuracy inside the thermowell as well. Do you have anything to add to that, Dietmar?
Yeah, again, the input of the audience, the baddest effect of the thermowell is the air gap in between. So if you order the combination of a thermowell and the measuring insert, consider that you go to the minimum air gap. That makes your measurement more accurate and much more faster. I often see a lot of standards that, yeah, we are using whatever because it's easy to install and deinstall if we have a big air gap. That might be true, but you will lose accuracy. So use the slimmest air gap you can order to increase the accuracy.
Yeah, and then once more, does the quality of the sensor matter and how accurate how accurate the temperature readings would be? It depends.
Yes.
The sensor class matters according to the inaccuracies. As soon as you have it matched to the transmitter, it doesn't matter anymore. But the sensor type matters because measuring the real value is something that Dietmar showed with the golden rules. You will get the presentation after the session together with the recording. So in case you have questions about certain topics, feel free to contact us at any time. And in the presentation, there is also the link how to directly contact our colleagues abroad, so directly in Australia. I think we have the QR code here, so I will disappear now.
Put away your head.
And therefore, once more, thanks all of you for being here, for asking all the questions. And last but not least, Dietmar.
Don't do this at home. Stay safe.
Don't do this at home. Bye.